Okay, so this is what I want to talk about: image noise. Okay, in general, digital images are prone to different kinds of noise. Noise can come in at the acquisition process or during some kind of compression or transmission. Okay, so there are many ways in which noise gets added to the image, and then the image quality is degraded. So, for a number of purposes, you would want to first remove the noise and then work with the image. So, noise essentially refers to some pixels which are not supposed to be there in the original image. They don't really reflect the actual intensity that should have been captured by the sensor. Okay, so these are spurious pixels, and so we want to see how noise can be modeled and what are the common filters or common methods in which you can remove that noise. Okay, so we will look at only two kinds of noise. These are the most common kinds, which is uh, so this is called these are classed as additive noise. Okay, so additive noise. I'll say in a moment why. So noise that can be described using a probability distribution function and periodic noise. So these are the two types that we look at, but there are also other types that can appear in different circumstances. Okay, but they require a more general mathematical model that we will not be looking at. So, in the simplest form, noise can be modeled as uh, a term that gets added to the original image. Okay, so as I've written here, so your degraded image is the original image plus some noise NXY. So this NXY itself can be displayed as an image, a separate. Okay, so if these two images are added, you get your degraded image. Okay, so this is a simple mathematical model. And when noise is added in this way to the original image, we will say this is additive noise. Okay, so these kind of noises which can be obtained or viewed as the original image plus some pixel values at different places. Okay, this is called as additive noise. There's a more general uh, model or a formulation for noise uh, in terms of a linear operator, but that is not yet what we will do. Okay? So additive noise, this is in this form, can be generally modeled by a random variable. So we are not, so as I said, we will talk about these two, right? So right now I'm talking about the first type, not periodic. Okay. So generally, additive noises which are not periodic can be considered to be modeled by a random variable that obeys some kind of probability distribution function. So if we have this assumption that we can, model noise by a PDF, then we can also create noise for simulation purposes using such PDFs. Okay. Uh, so first, so these are the most common types of noise PDFs, and we look at each of these. So there's Gaussian noise, Rayleigh noise, gamma noise, uniform noise. Then a special case of the uniform noise is exponential noise and salt and pepper noise. Okay.
Hello.
So I have sort of embedded this image from the book, which describes the PDF for each of these noises, okay, as you would expect. So here there is the formula for the PDF, probability distribution function, and its graph. Okay, this is the Gaussian PDF, and this is how the graph looks like. Here we have the Rayleigh PDF and the graph, and this is called gamma for a special case actually. In general, this is called the Erlang function. So the difference between these three, as you can see, is that the Gaussian, if you sort of squeeze it towards the left, you get Rayleigh, and you squeeze it more towards the y-axis, you get the Erlang function. Okay, so just keep these differences in mind, because when we look at the histograms, by looking at histograms, you generally can recognize what kind of noise it is. Okay. So these three and some more. So when this uh, Oh, sorry, I said something wrong here. A special case of the Erlang or the gamma is the exponential, not uniform. Yeah. So this one, if you take the special case with b equal to 1, you get this exponential function. Okay. The uniform function, as you would expect, this is the PDF corresponding to, or the graph corresponding to the uniform PDF. This is something that is new, which is the salt and pepper. This is called salt and pepper noise. Okay. So for the moment, you can forget this line in the middle, this V. Okay, we will see in examples what this is. But the point in salt and pepper is that uh, it it's called salt and pepper because the effect of this noise looks like you have randomly spread some salt and pepper granules on the image. Okay, so because of the way it appears, it's called salt and pepper noise. Okay, and its PDF is described by this PS. PS is the probability that a pixel is white. Salt stands for white, pepper for black. So PS is the probability that the pixel corresponds to salt, and PP is the probability that it corresponds to pepper or black. Okay, and so these are exactly telling you how many pixels or what percentage of the pixels are black and what percentage of the pixels are white. Okay, because see, this is the largest intensity value that can appear, right? This one you can forget for the time being. Okay, we don't need to focus on this. Okay, so just this is PP and PS. So once you know PP and PS, then you know what kind of noise it is. Okay, so PS for Z equal to 2 raised to K minus 1, PP for Z equal to 0. Okay, and the remaining for Z equal to some integer V. Okay, so actually this could be, so the remaining pixels we want to say are distributed in some other way. Okay, that is what this is saying. So this need not be exactly just one, there could be more of these. But for the time being, just focus on PS and PP. So this is salt and pepper. Okay, we'll talk more about this in a moment. So to understand all these kinds of noise better, we can look at the effect of all these types of noise on a simple test pattern, which consists of just 3 levels of intensities. Okay. So here are this first 3. So this is Gaussian noise, Rayleigh noise, and Erlang. Okay. Now, if you just look at these images like this, okay, there is no way you can make out the difference. I mean, by looking at the images, you cannot say what kind of noise is in the image, right? So for that, one has to always look at the histogram. Okay. See, what if we look at this original image, how should the histogram of this image look like? Correct. So there are just 3 bins here, and the pixels are distributed in these 3 bins, right? So I don't know exactly how many, but we can suppose something like this. This is actually the histogram of the original image, right? But now if you have this image, if you add a noise to this image, then the histogram looks like this. So the first one is the image with Gaussian noise. And we can tell that by looking at the shape of these. Okay, so these 3 straight lines. Oh, so they are actually saying that this is not white. Okay, the center is not white, is what that image tells us. So maybe we can draw the histogram of this image with the center being some K1, okay, some K1 intensity, K2, and K3, let's say. Okay, I'll not call it 255. Okay, and then these 3 values are there, intensity values, and we are binning all the pixels in these 3. So suppose this is the histogram of the original image, right? Then when with noise added to it, these 3 straight lines actually, because of the noise, the intensities are spread. Okay, now the shape of this spread gives us information, or we can glean from the shape itself what kind of noise has been added. Okay, so if you compare, so if you look at the first one, okay, this is quite symmetric about the center line, right? So the first one corresponds to Gaussian noise. Okay. Now, if you had just the second one to look at or just the third one to look at, maybe you would not have been able to guess straight away. Okay. But because now we are comparing, then we can see that compared to this one, in this second one, the histogram is slightly tilted to the left. Okay. So you can make a guess that this corresponds to Rayleigh noise. And in the third one, it's even more shifted to the left. So this should correspond to Erlang. Okay, but yeah, so you have to look at the histogram in order to understand this. By looking at the image, of course, you cannot uh, differentiate between these kinds of noise. Okay, and here are some more. So we can look at the histograms also. Okay, so this here we can see the graph is or the spread is shifted even more to the left. So this corresponds to exponential noise. Again, in the images, you cannot see much difference, or from the images you cannot guess, except the last one. Okay, by looking at this itself, you can say this is salt and pepper noise, because this is what exactly I described earlier, what it looks like. It looks like you have spread salt and pepper on the image. Okay, so the salt and pepper noise is one kind of noise that you can, guess by looking at the image itself. Okay, so this is exponential. We find this only by looking at the histogram. And this is uniform. And this is salt and pepper. And you can see how the histogram for salt and pepper looks like. So you have this some zeros and some ones here. Okay, so PS and PP. So that is a feature of and the remaining pixels are in these two bins. Okay, so that's a feature of salt and pepper. Okay, so is it? I mean, so these are the 6 kind of PDFs that correspond to various kinds of noise. And so now the question is how to remove this noise. Okay, so suppose you are given an image to process. It's a noisy image. Okay, so the first thing you do is you try to guess or try to find out what kind of noise it is by looking at the histogram. Okay, unless it's periodic, because periodic noise mostly you can just tell its periodic noise by looking at the image. Okay? In many cases, not all cases, but in many cases you can tell by looking at the image that this is periodic noise. Otherwise, you look at, first step, you look at the histogram. Okay, so if you have this kind of spread when you're actually expecting something like this in the original image, then you can guess that there is some noise. Also, I mean, even if you don't know that noise has been added, okay, how do you know an image is noisy? So this kind of, spikes that you see in the histogram usually will correspond to noise. Okay, this kind of spikes. So that tells you that there is some noise present in even these kind of spikes or jagged edges tell you that there is noise. Okay, so first thing, you have looked at the histogram. You've probably guessed what kind of noise is present. Then the next question is, how do you remove that noise? So there are various filters, and for removing additive noise that comes from a PDF like this, the most common way or preferred way is to use a spatial filter. Okay. Yeah. So this one would think that, okay, you have a degraded image, you simply subtract the noise from it, but you don't know what this noise is. That's the problem. Okay, so you cannot do this subtraction from GXY to obtain the original FXY. Okay, so that's what I have written here. So function recovery depends on being able to use the given image to figure out the mean and variance of the associated noise PDF. Why mean and variance? Well, because if you can find the mean and variance of that noise, then you can compute the PDF of whatever noise it is. If it's a Gaussian noise, then mean and variance are sufficient to compute that PDF. In the other kinds of noise, If you know mean and variance, you can compute these A and B's. Okay. So if you can compute from the image what is the mean and variance of the noise, then that helps you identify the PDF. Okay. So how to get this mean and variance? Okay. So if you have a noisy image, how do you calculate the mean and variance of what might be the PDF of the noise? So this is done by taking a patch or a strip in the image where the background pixels are of intensities that are not, too different from each other, almost constant. So you look at a background of almost constant intensity and pick up that patch of the image. So what will happen is that the in the original image, the intensities are not changing much. So whatever change is occurring because of the noise. Okay, so that kind of patch is a good place to look for noise, or to look at the noise in that patch and decide what PDF this might be coming from. Okay, so that is essentially what is being done. So what we'll do is let S denote a patch or a strip from the given image. Let PSZI denote. So we are essentially looking at the histogram for that strip. Okay, so PSZI is the probability estimates or the normalized histogram values of intensities of the pixels in S only. Okay, so for these three kinds of noise, okay, or not just these three, I think they have taken 1, 2, and this one 3. So from each of these images, they picked up a strip. Okay, so a strip from here, a strip from here, from these noisy images. And for each of those strips, the histogram has been calculated. Okay, so this is just an inset. This is not part of the histogram. Okay, this is just an inset of a strip of that noisy image. So for this strip, if you calculate the histogram, comes out to be like this. And for each of these, it comes out to be like this. So from this one, so of course, the histogram is not going to look like the previous one, right? It's not going to look like this, because right now we are looking at only one intensity. So there's going to be only one peak. Okay. So the remaining two are going to go away. Also, we'll not have the same height or size and shape as because we are looking at a different number of pixels. This is for this image, right? But if you look at the general shape of the histogram, then you can guess that this is a Gaussian. Okay. Similarly, you can guess that this is Rayleigh. Okay, and you can guess that this is uniform. So from a strip of the image, which satisfies this property that the background intensities are not too different from each other. So if you take a strip of the image like this and look at the noise or look at its histogram, then you can guess what kind of noise PDF is there in that image. Okay. And from that, you can work backwards. Okay. So if on this strip, you have this behavior Gaussian, that means in that image, there is Gaussian noise. Okay. And then you try to apply filters that will remove Gaussian noise. So this is how you can work backwards. Okay. Well, so if PSZ are the normalized histogram values in here, okay, for this strip, then the mean, I mean, you know the formula for the mean and variance once you know these histogram values, right? So the mean is given by this and the variance is given by this. Okay, once you know the mean and variance, you can calculate the PDF. Okay. Another point is that this approach will work for all PDFs except for the salt and pepper noise. Okay, where because in salt and pepper noise, you don't require just a guess like this. What you require is an actual estimate of PS and PP. Okay, so that you are not able to that you are not going to get from this strip. Okay, in this strip there might be a certain PS and PP, does not mean it's going to be the same for the entire image. So this method does not work for salt and pepper noise. However, with salt and pepper noise, it is just much more easy to visually guess that this is salt and pepper noise. Okay. And also, if you take the histogram of the entire image, that also makes your guess, I mean, can support your guess of salt and pepper noise. Okay, so you don't have to go with a strip like sorry. Okay, so now yeah, so the point was that if you want to denoise an image, one of these additive PDF noises, then the method of choice is using spatial filter. Okay, so I'm going to just list out all these various filters which are commonly used to remove such noise. Okay, so there are filters based on mean, filters based on the order statistic like median, max, min, midpoint, and there is one more that is the some alpha midpoint. And then there are many more. Okay, there are many adaptive filters. Adaptive means filters that you can come up for of image wise. Okay, so you are given an image, and according to the requirement of that particular image, you can come up with some combination of these earlier basic filters. Okay, and create your own adaptive filter. Okay, so there are many adaptive filters also. Okay, so let's look at just these basic ones. Okay, so we will only look at these basic filters, not at the adaptive filters. There are some in the textbook, and of course, there are many, many more. People keep coming up with various filters for various applications, especially in medical applications. Okay, medical imaging, that is one field where you cannot. Uh, Medical imaging is one field where there is no tolerance for error. So a lot of methods keep coming up in the medical imaging field, better and better methods, because the tolerance for error in medical diagnosis is very low. So you don't want to give the wrong diagnosis based on some image processing error, right? So there, all these the best methods in image processing and computer vision tend to come up in the medical imaging field. Okay, so yeah, so moving on. So I will just list all these filters, okay, and the main uses of, okay. So in all of these, in all of these formulae, SXY is a sub-image neighborhood. So so you have an image. SXY is a part in that image centered at the pixel X comma. Okay, so it's a sub-image neighborhood centered at XY. That's what SXY stands for in all these formulae. So the arithmetic mean filter. Okay, you can easily guess why the name is arithmetic mean. You're simply taking the arithmetic mean of all these values. Okay. By the way, GXY is the degraded image. Okay, so that's our earlier notation. G is the degraded image, and F hat is the restored image. Okay, so you're restoring the image by applying this filter. Okay, so what this filter is doing is it's looking at the neighborhood, taking the arithmetic mean of all values in that neighborhood, and placing that arithmetic mean at the center pixel XY. Okay, so that is what, and that is how all the filters work. These are all convolution filters. Okay, spatial filters. So the sum of products kind of operation is being applied for all of them. Okay, so the arithmetic mean filter is a basic filter that smooths local variation, and actually the noise removal happens because of the blurring action. Okay, so it essentially blurs, and so you feel like noise has reduced. Okay, the geometric mean filter works like the arithmetic mean filter, but it does the work a bit better. Okay, and it causes lesser loss of detail. So this blurring actually will cause some loss of detail, and the geometric mean filter causes less of it. Harmonic mean filter works well for salt noise, but it fails for pepper noise. What this means is that salt noise means there's only white dots, okay, and pepper noise means there's only black dots. So this kind of filter will work well for one kind of noise, but not for the other. But it does reasonably well for Gaussian noise. So these are just observations and places where these filters can be applied. There's also something called the contra harmonic mean filter, which is uh, which is this filter with some kind of order, okay, some order Q, and depending on various values of Q, you can get a family of contra-harmonic mean filters. If Q is less than 1, then this acts more like the harmonic mean filter. It eliminates salt noise, okay. And if Q is greater than 1, it eliminates pepper noise. But it cannot do both things at once. And when it eliminates salt noise, it does better than the harmonic mean filter. The median filter actually is one of the best filters for salt and pepper noise. Turns out that this is uh, best at removing salt and pepper noise. So this is not a sum of products kind of operation. Okay, so this filter, it just takes the median of all the elements in the neighborhood and places it at the center pixel. Okay, so this is not a sum of products operation anymore, whereas all the earlier were sum of products operations. The min and the max filter again. So these do exactly the. So the min filter, what it does is it finds the points with minimum intensity, which means it finds the darkest points, and it also erodes, which means reduces the bright areas adjacent to dark areas. Okay, so it sort of creates a shadow effect. Okay, the min filter does this, and the max filter creates a kind of brightening effect. It finds the brightest points and it also erodes the dark areas which are next to the bright ones. Okay, so that is what these two filters do. And then the midpoint and alpha trimmed midpoint filter. So I don't want to go too much into this anyway. Turns out that the midpoint filter works best for Gaussian and uniform mode. And this one, for varying values of D, these are filters that lie between the arithmetic mean filter and the median filter. Okay, so when D is 0, this is the arithmetic mean filter. And as D increases, you get closer and closer to the effect of a median filter. Okay, and it turns out that this works best on a combination of Gaussian and salt and pepper noise. If you have both these kind of noises present in your image. Okay, so these were just the basic noise models that follow a PDA. Then there is periodic noise. Okay, and we talked a little about periodic noise earlier when we saw the Moir pattern, right? So in general, periodic noise is kind of easy to guess, and this noise might correspond to periodic noise, some kind of. And the way to deal with periodic noise is to look at it in the frequency domain. Okay, so this periodic noise in this example is additive sinusoidal noise. Okay, so comes from a pure sine wave. And if you take the frequency spectrum, then it looks like this. Okay, so the center here, of course, is going to be the center of any frequency domain rectangle represents the average intensity of the image. Okay, so that is why you see this lighter pixels here. But these two dots are the ones that correspond to these this repeated signal. Okay, so if you can suppress these two dots here, then you will get rid of this periodic noise. Okay, so and like we saw in the Moir pattern, the way to suppress intensities in the frequency domain is to use some kind of a notch filter, right? So this was the definition of a notch filter. Okay, so I won't go into the details, but if you remember, then this HK and H minus K. So notch filters can be either Gaussian or Butterworth, okay, or ideal. And depending, so these HK will be either a Butterworth filter or a Gaussian or an ideal filter. Okay, and this is its sort of twin. Okay, And with these pairs, you can form a notch filter. So this notch filter will work on one spot. Okay, so if you have more than one spots to deal with, then you can create pairs of notch filters. Okay, so something like this. Okay, so you can, I mean, it's not too difficult. You just take more of these pairs. Okay, you add with more of these. So then that creates, so this one is an example of a notch filter with two, working in two spots at once. Okay. So essentially you can create notch filters like this, and what applying this notch filter to this kind of image, okay, will suppress these two intensities. So the effect is like, so this is your original image, this is in the frequency domain. You create a notch filter with a notch in these two places, okay, or a Butterworth or a Gaussian in these two spots, okay. When you apply it to the original, if when you apply it to the DFT of the original image, then and apply inverse to the processed image, and this is what the image will look like. Okay, so the all the periodic noise has been removed by processing in the frequency domain. So this is typically how periodic noise is dealt with. Okay, so in this image, it was clear that there is periodic noise. In some images, it may not be so clear. For example, here. Okay, so in this image, there is some noise, and but you won't be able to tell it by looking at the image at all. Okay, but so the frequency domain is plotted, and all this, sorry, all this, okay, corresponds to noise. So you want to keep the intensity, but remove all this. So this is the kind of notch filter. Okay, so this is going to reject all the intensities coming on here and pass only the intensities that are in the middle. So this notch filter applied to the original function, original image, creates this image. Okay, so this noisy image has been denoised. Okay, uh, but the point now is that in the original image also the noise was not very clear. Turns out the noise pattern is something like this. Okay, and of course you will not be able to tell this by looking at the image. You can tell this only by uh, processing or looking at the frequency spectrum of a given image. Okay. All right, so thus these two kind of noises that I wanted to talk about, PDFs and periodic.